The next step of chutzpah, of hubris, was to apply this theory to the universe as a whole. And to try to come up with a theory of the space-time of the universe. Not only the space-time around the star or the space-time near a galaxy, but the actual space-time of the universe. At this point, we really begin to get a scientific theory of the universe. Not of the matter, like the galaxies spread within a given space-time of the universe, but the actual theory of the universe as a whole, the space and the time and the matter and the energy. There's something that's very radical that comes out from this concept. If space warps sufficiently, what can happen is that it closes. What that means is, just like the planet Earth is round, if you go in one direction and come back to the same place, if you go straight in space, not because you're making a circle like on the Earth, but you really go straight, you go long enough, you'll come back to the same place. Now, how could that be? It's impossible, but it's not impossible. Mathematicians showed that it's entirely consistent with mathematics that this should be the case in mathematics. Physicists then wondered, one second, if this is logically consistent, can it be that our physical space also has the same properties? And Einstein's theory showed that not only that it can, but that it does, and he came up with an equation that shows by how much. And the solution to his equations showed that it's very possible that our universe is in fact finite in size. That it's not that there's a ball out there, and it's not that it's infinite, but it's so heavily curved by the presence of all the massing that even if you go in a straight line, you will come back to where you started, in whatever direction you went. And this was a radical philosophical innovation. We did not anymore have to think of the universe as being infinite in extent. It wasn't a paradox anymore. It could be that the universe is finite. Now, something very radical that came out of this theory was the idea of the finitude or infinitude of the space of the universe that we spoke about earlier. In a mathematical space, there's no contradiction involved if one says that a mathematical space is finite in extent, it's not infinite. And in other words, one can go in this mathematical space in any direction and come back to the starting point without saying that it's a, for example, if you have a sphere, right? If you go on the surface of the Earth, you'll always come back to the same point. You go straight all the time. But we know, of course, you're not going straight. We know you're going around in a circle because the Earth is spherical, right? Because we can see it from the outside. But a mathematical space talks about all the space that there is. Not that you're talking about some limited part of the space which is actually circular, and that's why you're going in a circle. But the space itself is warped so that if you go straight in that mathematical space, you come back to the same point. And the physical universe was shown to be also possibly the same. So that in whichever direction you went in space, you could come back to the same point without ever reaching a wall. Not because we are in some larger space where if you stood there, you would see that we're in some kind of sphere. But all the space there is, spatial relations are warped. And it's a staggering concept. But there's absolutely no paradox involved. We're just used to a flat space and to parallel lines not meeting and to having things come back to themselves only if you can see that it's a sphere. Now, what this meant is one of the major conundrums about the universe was shown to be not a problem. The universe doesn't have to be infinite. And basically, what turns out is that one can imagine, and this is something that you have to use an intuition that kind of develops with time, to understand how it could be, kind of like in a video game or any kind of screen where something goes off one edge and comes off the other edge. If you can imagine space having the property that it is warped, curved, whatever word you want to use, so that there's no actual ending. It's not like a screen which has a finite ending, and here's one end, here's another end, and you go off here, you come here. But there is no end. But on the other hand, it is not infinite. It's warped in such a way that if you go in the same direction, you will eventually come back to where you started from without ever having passed some kind of wall or boundary. Now it sounds impossible, but mathematically one can construct sets which have these properties, and it's all self-consistent, and it works. And therefore there's absolutely no reason why it can't be that space, physical space, has the same properties. And Einstein's model proposed something like this, which then was a solution. Now, it doesn't mean that cosmologists today necessarily assume that the universe is finite, but this was a way in which science was able to come up with a solution, a resolution of a conundrum that plagued humanity for thousands of years.